Hello, class. Yeah, 300 subscribers. I seem to go between 299 and 301 or something like that. Meow. 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 Oh, meow meow. Meow meow. Meow. Meow meow. Yay, meow meow. Comatose doggo. Hazel. 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 No. Oh man, you guys are slow to log on. Only 13 viewers. I'm marking everyone tardy. You think I should do that, Ivan? Ivan thinks I should do it. Okay, I'm going to get started. So I wanted to start off with a little challenge question, in quotes. It's not that challenging, but might make you think about simple harmonic motion a little bit. So here is a quote challenge question. And so let's suppose you have a particle undergoes SHM with amplitude A. What is the distance traveled by the particle over one period? So if you think you know the answer to that, go ahead and type it into the chat. So one full period. So while I'm waiting for someone to type something in so we can discuss that, I wanted to just briefly review what I did last time. So last time we talked about energy and the mass spring system. And so what we learned is that when a mass spring system undergoes, so 0 meters would be the displacement over one full period, but I want to know what is the distance traveled over one full period. So basically what we learned is that simple harmonic motion is an exchange between potential and kinetic energy back and forth, back and forth, back and forth. And for the mass spring system, it is an exchange between elastic potential energy and kinetic energy over and over again. Okay? And so the total energy, because it's an exchange between elastic potential and kinetic, the total energy of the system is potential energy plus the kinetic energy. All right. So this is the energy evaluated at any general point. Oh, man. So that before I continue, I'll just talk about the challenge question. The correct answer is 4A. Why is that? Well, if here is x equals 0, the equilibrium point, simple harmonic motion is going to go between x equals plus a and x equals minus a. So if you do one full period, it means you go back, you go across, and then you come back to where you started. So you go a distance a, 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 a. So that's 4a to go back and forth. So to go across is 2a, but then to come back, you go another 2a. So there you go. So this was how we evaluated the energy at any general point. But we know that basically what happens is when you are at the extreme points, your energy is all elastic potential. Why is that? Because if you were here at the extreme point and you had kinetic energy left, you would keep going. And so that wouldn't have been the extreme point, would it? Similarly, if you're over here and you still had kinetic energy when you arrived here, you would keep going past that point. So it wouldn't be the extreme point. So if we evaluate the energy at the extreme point, it is all kinetic energy, or elastic potential energy. And your position is equal to the amplitude. So that is the form of the energy evaluated at the extreme point. Okay. We could also evaluate the energy while passing through equilibrium. Now, when you pass through equilibrium, you have x equals 0. So that means that the potential energy term is gone, and we have all kinetic energy. If your energy is all kinetic, then that means that you are at your maximum speed, because if you were going any faster, you can't be going any faster than when all your energy is kinetic. So evaluating the energy while passing through equilibrium, we get that the energy takes the form of all kinetic and that your speed is the maximum speed. So this is while passing through equilibrium. Okay? So that is what we learned last time. And also, because the energy is constant for a simple harmonic motion, we can set any two of these equal to each other. So that is basically what we're going to do today, is we're going to develop some equations that come from conservation of energy. So I'm going to start out with the most important one, which comes from setting the energy at a general point equal to the energy at the extreme point. So if we do that, we get 1/2 kx squared plus 1/2 mv squared equals 1/2 ka squared. So let's play around with this equation. First of all, we notice that every term has 1/2 in it. So we can cancel out the 1/2s. And then I'm going to subtract the kx term to the other side. So I have mv squared equals ka squared minus kx squared. Now I'm going to factor out a k on the right-hand side. So I have k times the quantity, a squared minus x squared. Notice how you square them and then square each one individually and then subtract. Don't subtract and then square. Okay. Then I'm going to divide both sides by m. And then take the square root of both sides. Okay, so this is our first equation for today. First new equation. It's not really new, it's just a rearrangement of energy conservation. But this equation is really useful because it gives the speed as a function of position. Okay, right? Because we have speed on the left-hand side and we have position on the right-hand side. So this equation is really nice because we could say, for example, what is the speed of the particle when it's right there? All right, so that's going to allow us to calculate the speed when it's right there. So that's pretty nice. If you were to do a graph of speed v versus position x, so here's x equals 0, and we'll say here is x equals a. When the position is 0, you are passing through equilibrium, so you have your maximum speed when you are at equilibrium. So that's a point on this graph. And then when you're at the extreme point, your speed is 0. And then so these two connect to each other. It's not in a linear way. It's according to this relationship, which is this is actually the equation of an ellipse. So it kind of does like, looks like part of an oval. Kind of like this. Like so. All right, so that's a nice equation. That's really useful. We could get another equation by setting the energy at the extreme point equal to the energy while passing through equilibrium. So we could say 1/2 ka squared equals 1/2 mv max squared. All right. And so once again, the 1/2s cancel out. I could divide both sides by m, so I have k over m times a squared equals v max squared. All right. And then I take the square root of both sides. And I get square root of k over m times the amplitude. Please notice that in this equation, it's only the k over m that are square rooted in, not the amplitude, equals v max. All right. So basically what this equation says is that the bigger the amplitude is, the faster you're going to be going as you pass through equilibrium. Okay? That makes perfect sense. You're pulling the mass further from equilibrium. That spring is being stretched more. So it's storing more elastic potential energy. So when you get to equilibrium, you have that much more kinetic energy. Okay? Bugger's being a donut hole right now. Donut hole bugger. Hey, bugger. Bugger! Bugger! It was raining this morning, so the cat went outside for like 4 seconds. And he doesn't understand the concept of weather. So he goes out and it's raining and he runs back inside. And then, like, literally a minute later, he's like, okay, can I go outside again? And then don't do that. And then I let him outside again. He goes outside for like 2 seconds, comes back inside, and it just repeats. He just doesn't understand that weather doesn't change that fast. It's amusing. Okay, so there's another equation we could get by setting the energy at a general point equal to the energy while passing through equilibrium. So that would be an equation like, 1/2 kx squared plus 1/2 mv squared equals 1/2 mv max squared. And we could take that and we could solve for something. So you can do that yourself, but because all this is just equations that come from conservation of energy. There is one equation I wanted to teach you guys that does not come from conservation of energy. It comes from Newton's second law. So this is another equation. So we start out with Newton's second law, and then we realize that this is a mass spring system. So the net force is going to be the elastic force, negative kx. Okay, so negative kx equals ma. And then I'm going to divide both sides by m. I get minus k over m times x equals a. And so what we can use this equation for is we can figure out what is the maximum acceleration of the particle. So this equation says that the further you are from equilibrium, okay, if we want to make the acceleration go up, we have to make the position become as negative as possible because of this negative sign right here, okay? So the more negative we make the position, the bigger the acceleration is going to get. And if we just look at this picture I drew up here, simple harmonic motion is between plus a and minus a. So we'll get the biggest acceleration when x is the most negative, which is at negative amplitude. So I'm going to plug in x equals -1 amplitude. The negatives cancel out, and I get that the biggest acceleration is k over m times the amplitude. Please be aware that lowercase a represents acceleration, uppercase a represents amplitude. Those are two completely different things, okay? Amplitude is measured in meters, acceleration is measured in meters per second squared. So we're going to do a couple of examples that illustrate the use of these equations. It's pretty straightforward. All right. So a 2 kilogram mass is connected to a spring of stiffness 150 newtons per meter. The mass is pulled 0.3 meters from equilibrium and released from rest. Okay, so let's go ahead and parse these sentences here and figure out the information. So obviously 2 kilograms, that's obviously the mass. Spring of stiffness 150 newtons per meter. So if you don't remember, stiffness is the variable K. So that's K. And then when we say that the mass is pulled 0.3 meters from equilibrium and released from rest, that is telling us that 0.3 meters is the amplitude. Okay? Because remember, the extreme points are the only points in simple harmonic motion where your velocity is 0. Okay? So that means if you're at rest that far away from equilibrium, then that must be the amplitude. Okay? So we can just go through and just start using the equation. So that's what I'm going to do. So the first thing I want to do is I'm going to calculate the period. So the period is 2 pi square root of m over k. So that's going to be 2 pi square root of mass is 2, stiffness is 150, like that. Plug it into your calculator. All right, I'm doing the same. I'm just reading the examples off the last class period, so I'm not going to do that. So I already know that the answer is 0.73 seconds. Okay. We could figure out the maximum speed. The max speed is going to be square root of k over m times the amplitude. So that is going to be square root of 150 over 2 times 0.3, which is equal to 2.6 meters per second. So that is the maximum speed. Okay. We could calculate the maximum acceleration. That is going to be k over m times the amplitude. So 150 over 2 times 0.3, which is going to be 22.5 meters per second squared is the maximum acceleration. So hopefully you're seeing that mass spring system, it's a very, the concepts are a little bit challenging, but the problems boil down to pretty much just using the equations, all right? So it's really not that bad. So here's a question. It's a little bit of a trick question. What is the speed of the mass when 0.4 meters from equilibrium? So I want you to type into the chat. You don't have to do any math for this question. I want you to type into the chat what the answer is and why. Okay? So while I wait for you to type that in, I'm going to go to the next question, which is, what is the speed when 0.2 meters from equilibrium? All right. So for this question, I have v equals square root of k over m times square root of a squared minus x squared. I find this to be the most useful of the equations that we learned today. Oh, very good. So, yeah, so you're on the right track there. Let me finish this up and then I'll go back to part D. So I have square root of 150 over 2 times the square root of a squared, the amplitude is 0.3, minus the particular position where we want to calculate the speed, which is 0.2 meters. Remember, you're squaring each of these individually and then subtracting them, okay? So when you work that out in your calculator, you get 1.94 meters per second. Now this is good. Okay, there's a little sanity check, which is this speed had better be less than the maximum speed. If you found that it is greater than the maximum speed, like maybe you got 3 meters per second, you would want to scratch your noggin and go back to the drawing board and figure out what you did wrong. So this is less than 2.6 meters per second. Very good. Okay. So going back to part D, the comment in the chat is correct. It is not possible to get to 0.4, at least without giving the system more energy. Okay. Why is that? Well, because simple harmonic motion is bounded motion. It's between plus a and minus a. So if your amplitude is 0.3 meters, 0.4 meters is out here, which is out of bounds. Okay? So you can never get there. You could never get to 0.4 meters. So this does not exist. Undefined. It's kind of fun to see how does the math work out in this case. So we could try to apply this equation, square root of k over m times square root of a squared minus x squared. And when we do this square root part, the amplitude is 0.3, so we'd have 0.3 squared minus, and then the x value where we want to calculate the speed is 0.4. So 0.4 is bigger than 0.3, so when we square them and subtract, we get a number that is less than 0, which we then have to take the square root of. So basically, if you tried to calculate this with equations, you would get an imaginary speed, which is not possible. The speed is very real, okay? So that's what happens. Let's do one more example. I want to show you something that's maybe a little bit more complicated to show how so usually what happens in physics is it gets more complicated when you start bringing in multiple areas of physics, okay? So I'm going to show you a problem that brings in momentum into a simple harmonic motion problem. So, excuse me. Suppose we have a mass that's connected to a spring. The spring has a stiffness of 100 newtons per meter, and it's a 2 kilogram mass. And it's sitting at its equilibrium position at rest. Okay? It's sitting at its equilibrium position at rest. So, because it's at its equilibrium position and it's at rest, it's just going to stay there forever if it's undisturbed. But what if we decided to disturb the system by sliding a 1 kilogram mass at it. So we slide this 1 kilogram mass to the left at 30 meters per second. Okay? And so obviously this 1 kilogram mass is going to collide with the 2 kilogram mass, and that's going to start the system undergoing simple harmonic motion. So let's suppose that they have a completely inelastic collision. So if you recall, a completely inelastic collision means that they collide and stick. Okay? So anytime there's a collision, momentum is going to come into play. So first of all, let's figure out what is the period. The period is 2 pi square root of m over k. Now, your knee-jerk reaction might be to use m equals 2. But once they collide, it's both of them that are now oscillating because they're stuck together. So the mass that I should use is the total amount of mass that's going back and forth, which is 2 kilograms plus the 1 kilogram that collided with it, so 3 kilograms. Okay. I didn't actually work this out last period, so let me go ahead and do the numbers here. So that's going to be about 1.1 seconds is the period. And then from that, we could figure out, well, not from that, but what if we wanted to know what is the maximum speed? Well, basically, so the 1 kilogram mass comes in, collides, and then they start oscillating together. All right? And if we think about it, after the 1 kilogram mass collides, they're going to start moving to the left. Okay? And that's going to start compressing the spring, which is going to slow them down. So the maximum speed, because once they collide, the spring is immediately going to start to slow them down. So the max speed is the speed just after collision. Okay? The maximum speed is the speed just after collision. So how do we get the speed just after collision? We would use momentum. So I would say P initial equals P final. I'm going to have going to the left as positive for this problem, just for simplicity. So initially, we have 1 kilogram moving in the positive direction at 30 meters per second. I'm using the fact that P equals mv, if you don't remember. So mass times velocity. And then after the collision, they're stuck together. So they're acting like a single 3 kilogram mass with a certain final velocity. So dividing both sides by 3 is going to give me that the final velocity is 10 meters per second, and that is the maximum speed. So Vmax is 10 meters per second. All right? So now, what if I wanted to determine the amplitude of the resulting simple harmonic motion? Well, again, I would go to my equation for Vmax equals root k over m times a. So this equation goes both ways. We can use it to solve for Vmax, or if we know Vmax, we can use it to solve for the amplitude. So we can say the maximum speed is 10, and that equals square root of k, which is 100, and mass, which is, again, 3, because that's the amount of mass moving, times the amplitude. So let me work that out. And that means that the amplitude is 1.73 meters. And we could go on and ask more of the same stuff that we did up here. But really the trick is using momentum to figure out Vmax, and then recognizing that it's not 2 kilograms going back and forth, but in this case, it is 3. Okay? So I'm almost done here. I did want to talk a little bit. This lesson has been about energy and the mass spring system. But we learned about 2 simple harmonic motion systems. The other one was the simple pendulum. So what if we have, let's just talk really briefly about energy and the simple pendulum. Okay, so to remind you, a simple pendulum is you have like a ceiling, and you have a mass that is on the end of a string. The string has length L, the mass is M. And so because the string is not, you can't extend the string, as it swings back and forth, it's going to go in a circular arc, like this. Okay. So at some later time, the mass will be over here. Man, you're being very disruptive today, dude. He's like, I'm supposed to be outside right now. So if we're over here at the extreme point, notice how, because it's moving in this circular arc, if this is y equals 0, wow, I totally messed that up. That doesn't look horizontal at all. So you're at y equals 0 at your lowest point. When you swing, because you're moving in this circular arc, you actually have an elevation. Okay? So, Ivan, don't do that. Driving me nuts today. So basically, the lesson is a simple pendulum is an exchange between kinetic energy and not elastic potential energy, but gravitational potential energy. Okay? So whereas the mass spring system is kinetic to elastic to kinetic to elastic to kinetic to elastic, a simple pendulum is kinetic to gravitational to kinetic to gravitational to kinetic to gravitational. Okay? And so our energy equation, so the total energy of the simple pendulum is going to be 1/2 mv squared plus mgy, because that is the gravitational potential energy. So this is the energy evaluated at a general point, so anywhere in the motion of the pendulum. If we chose to evaluate the energy at the extreme point, then again, you have no speed at this extreme point. So you're going to have as much gravitational potential energy as you can have, which means that you're going to be at your maximum height. So, so your energy is going to be 1/2, mgy max. So this is evaluating the energy at the extreme point. And then as we return to equilibrium being straight up and down, the pendulum is going to pick up kinetic energy as it loses gravitational potential energy. So 1/2 mv max squared is the energy evaluated while passing through equilibrium. Okay, so this is how all of this relates to the simple pendulum. And we could go through and we could do all the same derivations, all right, that we did for the mass spring system, but we're not going to do that. All right, so that is my lesson for today, class, and I will see you